Hello everyone, I hope you guys are doing great. In this lecture, I'm going to discuss about MNIST dataset, which is the handwritten digits dataset. So we are going to understand how the data looks and how to write convolutional neural networks, how to plot a confusion matrix, how to find the error outputs and predict them, and that's not all. So at the end of this lecture, I'm going to give you step by instructions to make your own handwritten data image and how to predict it in TensorFlow. So it's going to be a really fun application. So here's the deal. So I've used a higher level API of TensorFlow, which is the TFLearn. I request you all to download and install in your system. It's just it takes a line, just pip install TFLearn. It's the reason is it saves a lot of time and effort. I'll justify more about using TensorFlow at the end, but right now I request you to install this. So let's get started. Before we get started, we have to install TFLearn first. You can go to tflearn.org, go to click installation. Once you install TensorFlow, install the stable version of TFLearn. TFLearn has a lots of options as you can see, but I'm just going to restrict myself with using code layers and convolutional layers. The very first thing is import all the necessary function. Import NumPy, Matplotlib, TensorFlow. These are basic functions we need. And I'm importing confusion matrix from sklearn.metrics in order to plot confusion matrix, and to create a montage, I'm importing montage2D function from skimage. These two are optional, but I really recommend you to install and import these two because confusion matrix gives a very good idea about what's going wrong, and montage gives a very nice view of input data. And import tflearn, which I've just installed, and Python imaging library to plot show the image which are our own handwritten data. And I'm going to use inline plot to plot inside IPython console. And the second step is to import data. So you don't have to separately download MNIST data. The good thing about TensorFlow, it already has provided a helper function to download and extract the data. So all you need to do is to import the function import data, which lies in TensorFlow examples tutorials.mnist. One important thing is when you're importing, please make sure that you include one-hot encoding. What this means is once you have the output class, so it will return an array of zeros and ones, and one corresponding to that particular class. If you choose it as false, it will just return a single value denoting the class name. That is, if image is 7, so the output class will be just 7 if in case of one hot is false. If you choose one hot as true, so you'll have an array of 10 numbers, and if the class is 7, so in the 7th 8th column you'll have a 1 and the rest will be 0. You have it in 8th column because it starts with 0. So moving on, let's see the shape of a data set. As you might have noticed, the data set has three different splits: training data set, testing data set, and the validation data set. The reason for these three different splits is we need our training data set to train our model. We need a testing data set to measure the accuracy on unseen examples in the training data set, and whether it performs well or not. In case if it doesn't perform well, we tune the hyperparameters and again measure test set accuracy till we are satisfied. So once we are satisfied with the training dataset error and test set accuracy, we need to again have another dataset to measure the performance on unseen examples, because we used both training and testing, and we need the third validation dataset to expose our network on unseen dataset, and finally measure the accuracy of the validation dataset. So let's look into the shape of our data. So the training dataset contains 55,000 images. So each and every image reshaped from 28 by 28 pixel into a single vector. So each and every row is concatenated, and I have 784 pixels. So the dimension here is 784, and the classes would be 10. They are denoting the numbers 0 to 9, and we have 10,000 data in testing dataset, and 5,000 in the validation dataset. So let's look a sample of how a data set looks. So I'm going to pick the fifth image in a training data set. I'll reshape into 28 by 28 pixels and plot it. So this is number 8. So to have a broader look of our input data, I've created a montage of all the first 100 images in the training data set. So these are different numbers in our training data set. So this is how our training data set looks. The next important thing about our data visualization is to visualize mean and standard deviation. So here I have calculated the mean and standard deviation of the training data set. So this is a mean image. So this gives an idea about our image. So most of the blue region is the background region. It's 0, and here there's a heavily concentrated. So all our numbers more or less appear in this particular rectangular box, heavily concentrated on the center. Another interesting visualization is of the standard deviation of our data. So here you can see how many numbers kind of deviate from the mean. So the major concentration is again in the center, and almost negligible in the background. So in these places there's no any deviation, and so we have to concentrate on the center. So this is just a visualization of our data. Moving forward, let's initialize our TensorFlow graph. So here I'm giving x to be the input placeholder. So as we know, in our training dataset we have 784 is the dimension of the input vector, and this can be anything basically. So because depending on the batch size you will be feeding, so you can safely give it as none. So you can feed in as many images as per you like, and the class is 10. So again, since your batch size is not fixed, it's always good to say give the first dimension as none. So basically you're instructing the TensorFlow to calculate dynamically the shape of this particular dimension. So my input image is of 784, and the corresponding input class is of dimension 10, corresponding to 10 digits 0 to 9, and this corresponds to each and every image, 28 by 28 pixel image. So model definition. So I'm going to use a convolutional neural network in this particular example. So I have chosen first my input layer, and followed by two convolutional layer, and fully connected layer, and a softmax layer. So each and every single convolutional layer consists of a convolutional operation and followed by a nonlinear activation function and finally a pooling layer. So please note that I have used stride of 1 and in the convolutional layer, because since I'm using max pooling layer also, so the dimensions will be halved. So let's go and define. So in case of uh, convolutional operations, you need to have 4D tensors to feed into a TensorFlow graph. So this is the dimension of our image, 28 by 28. This stands for the uh, number of channels. So here it's a grayscale image, so it's 1. So again, this is the batch size or something. So you can safely give it as -1. So this is our input. So I'm reshaping our input to this to feed into a convolutional layer. So here I have defined my first convolutional layer using TF-learn's function. So from in case of convolutional 2D operations, you have this function inside TF-learn's layers convolutional and then convolutional 2D operation. So I'm inputting my 4D tensor, which is X input in here. I'm using 32 filters of size 5 into 5. So you can choose as per your wish. You just easily you change like 64 or 128. It's up to you. And filter size 3 into 3 or 5 into 5. So choose your own filter size. So here I'm giving a stride 1 because I'm also including a pooling layer. So here the dimensions are going to be the same in this particular operation, convolutional operation, and followed by I'm going to give a nonlinear activation function, which is ReLU, rectified linear unit activation function, and just using L2 regularizer. Basically, we use regularizing to reduce the generalization error and not on the test error, training set error. And I'm just giving a name convolutional layer 1. So after we pass the convolutional layer, I'm giving defining a max pooling layer. So it takes the maximum in the neighboring 2 into 2 matrix. So the dimensions will be halved. So my input is 28 cross 28 and single channel. So my output should be 32 filters, and since I've given 2, it will be 14 cross 14. Again, none cross 14 cross 14 into 32. 32 denotes the number of filters. So similarly, I define my second convolutional layer with the same 32 filters and filter size 5, stride 1, and followed by max pooling layer. Now I have what I have is uh, 32 filters and 7 by 7 images. So in order to find out our softmax layer, in order to provide input, we need to have a fully connected layer. So I'm going to define a fully connected layer here. Again, I've used TF-learn to do this. So if you're using TensorFlow, again it's a bit cumbersome because you have to find the shapes and dimensions of the image layer and multiply with the number of filters. So it's easy, but when you have a very big model, it becomes really cumbersome. So TF-learn comes very handy here. So just importing fully connected layer from TF-learn's layers.core. So I'm taking the input as the output of the second convolutional layer after max pooling. So I have 1024 neurons, and again I'm using activation as a ReLU. So the input will be this convolutional layer, output of this convolutional layer, and I have 1024 neurons. So I have also defined a dropout layer. So dropout primarily reduces the case of overfitting. Excuse me. So once followed by dropout layer, I'm going to connect this to my softmax layer. So I'm going to take the input output of my dropout layer and then uh, feed into my softmax layer, and this returns me an array of 10 corresponding to the number of classes. So here we have the number of classes as 10, so it's going to be 10 outputs. So let's have a look into our shape of our model. So the shape of the input layer is none, 28 by 28 and single channel. It's a grayscale image, so it just has a 1. And shape of my first convolutional layer, this is after max pooling layers, so it's halved, the dimensions are halved. I have 32 filters, meaning 32 channels, so I have 32 channels. Second convolutional layer takes the input from the first convolutional layer, so again at the end the output is again halved. From 14 it's cross 14, it's 7 by 7, and again I've chosen 32 filters, so it's going to be 32 filters here. So I have 1024 neurons in my fully connected layer, so the output is 1024, and in my output layer it's a softmax layer with 10 neurons corresponding to the 10 classifications, so my output is 10. Moving on, I'm going to define my loss function. So I've used maximum likelihood loss function. So this is my actual class and the predicted class. So I have chosen to be calculate this particular sum, the product of this sum, and calculate the sum and then reduce it, and calculate the mean, and in my training step I'm going to reduce this particular sum. So the trick here is, in case of maximum likelihood, we are trying to increase the product of the true class with the predicted class. So I have taken a negative sign here because I'm trying to uh, basically minimize in my training functions. So the trick here is, the maximum of a function is equivalent to the minimum of the negative of the function. So it's just the same. Multiplied with a minus sign over here, taken the sum, I've taken the mean. First I've taken the sum and then I've taken the mean, and then I am using Adam optimizer here to minimize my loss, and then I would like to calculate my prediction and accuracy here. So first I calculate how many of my predicted is equivalent to the actual class, and then I calculate my accuracy. Since I'm in a IPython console, I've given a interactive session. Since I'm in a IPython console, I've defined interactive section over here. I'm initializing all the variables over here, these two statements. Now, so our graph is initialized, all the variables are initialized. So let's look into the operations in our graph. So this particular command gives us all the operations that we have declared. I have declared a weight inside the convolutional layer, bias, and this is for second convolutional layer, first convolutional layer, the fully connected layer for initializing the weights, and the dropout layer, and finally our output layer. And this is for calculating all the gradients. Okay. Moving on, I have defined the number of iterations to be epochs to be 15,000 iterations with a batch size of 50. So every iteration I'm going to send 50 images. So uh, this is my for loop where I run my program. I feed in every 50 images. So this is my data is the variable that I have given from the input. So data contains all the things. So I'm going to feed in images and the corresponding classes, and every batch corresponds to a batch size of 50. So you can easily select with the input data function itself, data.train.next. Data is the input data object, and it contains the training object as well. Inside you can find a nice function called next batch, and how much ever we want to feed, we can feed in our size. So I'm going to plot my accuracy for every 500 iterations, and for every 100 iterations I'm going to plot my loss. So my very first iteration have a loss of 2.28 and so, and the accuracy on the test set is 11.8. We have some accuracy level of accuracy because I've already sent 50 data points, and as you see, like the loss also goes down and the accuracy on a test data set goes on increasing. So this could take a while depending on your system configuration. So from nearly 11.18% in the first iteration, it goes 94, 96, and it shoots above 98%, 99% actually. So you can run as long, but make sure that you don't overfit your data. Anything about 99, it's really good. Yes. And what's more important is the performance of our model in the validation data set. So you can again, I'm checking the accuracy in the validation data set. It's 99.14, which is really good. In case if you're having a very poor accuracy on a test data set, but you have a very low loss in a training data set, you can go back and change the hyperparameters. So basically try to here the hyperparameters, for example, could be the number of filters here, number of convolutional layers here, or number of neurons in the fully connected layer, so and so on. So my validation accuracy is also pretty good. So moving on, I'm going to store all the predictions in the test data set for my future analysis. So I'm going to run this time, but I'm going to just pass on the images, and it will return the y predicted. Y predicted is the last layer. Basically, it's the output of a function. Output of a model. Let's go and plot our confusion matrix. First, we need to find the true class and the predicted class. So the arrays containing the data dot test dot labels and y test basically are arrays containing zeros and ones. So data dot test dot labels contain zeros and ones, and one corresponding to that particular class. So once I pull out the argument of the maximum value, it gives me the true class, and in case of predicted class, y test contains the probabilities of different digits, so different classes. So the maximum, the value with the maximum, and gives the value of that particular class, and the helper function argument max calculates the maximum value, basically the index, which is the class. So the predicted class will be np dot argument max of the predicted function. Now let's go and plot the confusion matrix. I've imported this function earlier. So my confusion matrix is in sklearn.matrix. So this is my confusion matrix, and better plot of my confusion matrix would be here. So this is a nice plot of my confusion matrix. This is the predicted label, and this is the true label. The next step in our analysis is to find where our model has predicted incorrectly and plot them. So first I'm finding the indices where my model has predicted incorrectly, and then I'm plotting them. So you can see these examples, majority of the mispredicted values are because of very poor handwriting. So, and for example here, it's very confusing to our own eyes whether it's 6 or 4. So the model predicts here 4, but the actual value is 6. And here again it's a very slanted 7, and here in case the digits are not complete, so the model predicted 2 and the actual class is 8. And here it more or less looks like 1 for some handwritings, and it's basically the actual value is true and the predicted is 1. And again this is looks like more like 1 even to our own eyes, but the actual is 7. It's very poorly written, 7 layer of 7. And here it's very closely spaced, and the true value and is 9 and the predicted is 4. So as you see, the majority of the cases of error is due to very poor handwriting. We have now completed our basic analysis of our model and evaluated its performance. What will be more interesting is to see how the different filters respond to a particular image. So first let's visualize the weights of the first convolutional layer. Then we'll try to pass on an image and see how these filters visualize our input image. Let's first see the shape of the first convolutional layer. So I'm going to import the values of the first convolutional layer and declare it to its filters. So the shape is 5 cross 5 into 1 into 32. So 5 cross 5 corresponds to the filter size. So earlier I had given 5, the filter size of 5. So 1 corresponds to the number of input channels and 32 corresponds to the number of output channels. So I've given 32 channels as my filter number of filters, so it's 32 here. I've reshaped into 5 cross 5 into 32 because 1 doesn't play any role here. And now I have plotted my 32 different filters. So this is how each and every filter looks. So this is what my model has learned from the data set. So let's now feed in our input image. So I'm taken my very first image in the test data set, and I'll pass it through my network and then see what's the output. So this is my test image, and I'm going to pass it my test image and uh, see the output of the first convolutional layer. So this is the output from the max pooling layer. So I've just plotted my test image. So the shape of the image after it goes through the first convolutional layer activation and the max pooling layer is 14 by 14 into 32. So it's 14 cross 14 now. I mean, from 28 to 28, it's downsampled to 14 cross 14, and we have 32 different channels here. So I've plotted all the different outputs from different filters corresponding to these filters, these 32 filters, how these filters convolve this image, and how the network sees. So this is a very nice visualization. So you see some filters focus more on the vertical edges, and some on the horizontal edges. So this is how our network sees our input image. Let's move on to the most interesting part of this lecture, drawing our own handwritten digit and testing it on our own network. So I'm going to use an open source package called GIMP to draw my image, and later I'm going to test it, and I'm going to show you how. A word of note, you can use any other software as well, but please make sure that you are choosing a grayscale option with black color background. In case your background is white, it will not work. So please take a note of it. I'm first importing my image that I've created in GIMP. So this is the image that I've just created, and this is how it looks. I've used the package from Python image library that we have imported earlier. And after importing, we need to resize it to 28 by 28. It's this particular image is 256 into 256. I need to resize it to 28 by 28 pixels. And after resizing, I'll convert into an array to perform some mathematical operations. I need to normalize it because the input data, the values go from 0 to 1, whereas here it goes from 0 to 255. Also, remember when you are normalizing it, be sure to choose as type float, because this would be an integer by integer division. It will turn out to be 0 for all. Uh, Once you make this particular value as float, for example, if the maximum value is 255, it will return it as 255.0, and divide my image, so it will be normalized from 0 to 1, and it's very important that you give it as a type float. Once you have normalized it, you need to reshape in the format of input tensor. So remember, in the placeholder I had given 784, 9 comma 784. So any input you're feeding into, any image we are feeding into the model has to be of the dimension 784. So I have reshaped it to 1 comma 784, this import image, and now I'm passing this particular test image into my model, and then calculating the predicted array. This will basically an array, of 10 values, uh, followed by calculating the maximum value of that particular array gives me the predicted class. Oh, who? So here you have seen that it calculated the predicted image as 7. Just to play around, I'm importing one more image over here. So this is how my image looks, and repeating the same steps and then feeding this particular value into my model, and then who the predicted class is 5. It's a lot more fun to test our model with our own handwritten images. So this brings us to the end of this session. I hope you guys enjoyed this session, and if you like my lecture, please subscribe to it and inform your friends as well. So a lot more lectures and tutorials are on the way. Signing off. Thank you.